today's topic is the smart pointers, chapter 15. So we can ask ourselves, what is the pointer, right? Seems like a trivial question, but in fact, I guess there are different definitions. But generally, the pointer itself is just a variable containing address to the memory. Then some people will say that might be also resource. And if we're talking about the smart pointers, then there is a data structure. Sorry, my boy is kicking me. Yeah, so the smart pointer is a data structure pretending to be a pointer. And in many cases, the smart pointer. Oh, I think, so that's not me drawing it. So the smart pointer is, in many cases, they own the data or resource pointed to. And on top of that, they have extra capabilities and they have extra metadata. So they're not just raw pointers, obviously. And can you see my screen and the yellow thing on the screen?
I'm not sure what you're talking about with regards to the yellow thing. I can't see.
All right. Okay, so if it's not you, that's cool. But on my screen, I see a yellow penis, unfortunately. Yeah.
Oh dear.
All right. If it's not seen to anyone else, that's cool. Yeah. So we already know some pointers, right? Smart pointers, and according to the book, they say that those pointers are string and the vector of a type, and any other types from the collection. And you already can see that this is not exactly according to the definition that I've just given about the smart pointers, that they pretend to be the pointers themselves, because neither the string nor the vector are trying to be the pointers, but they manage the resource and they're trying to establish some invariants around that resource. So the string is making sure that it holds a value to TF8 string, whereas the vector keeps, for instance, continuous elements in the continuous memory. The string and the vector are considered to be smart pointers, even though they don't pretend to be smart pointers, right? But half of the definition they do satisfy. And today we want to focus on 3 different types of smart pointers: box of a type, ref count, and RefCell. And so the important thing about those smart pointers that we're going to be talking about, they are not synced, meaning those are not thread safe. And that's good because we haven't gone yet through the we haven't gone yet through the threading, the concurrency, and there's no point for us discussing this. That I think is going to be in another chapter. All right, so let's go to the box. And yeah, so there is a box. Box creates values on the heap. So we know that Rust likes stack, like some other low-level languages. Box is also the only owner of the resource. And the box is really a special compiler type. So it doesn't implement some of the methods that we're going to be, or some of the traits that we're going to be talking about. But the compiler recognizes it and recognizes some of the annotations on the definition of the box, and then it injects its magic towards the box. And like, if we're considering how Rust behaves, for instance, if you have such a simple code like here with the structured point, then if we execute the code inside the main method, we go through the point construction, which basically creates on the stack 2 variables next to each other that they correspond to the layout of the point. Then it creates an array of the 5 elements with the ones. Then you can access them, printing them. And once you reach out the end of the scope, those are going to be removed in the reverse order that they were constructed. So that's accessing the stack and none of the heap. But if you were to use some of the heap, then you would be using obviously box, because we're talking about it. And in such a circumstance, when you're trying to create a point inside the new box, what will happen is that the small part of the box will be created on the stack, but then the box will also create a point structure on the heap that it will references. Then again, a same size box structure will be created on the stack, but somewhere else on the heap, according to whatever allocator the current Rust is using. So it will create an array object on the heap being referenced by that box. You would be able to access them, and you would be able to access them in different way. For instance, by dereferencing them, and we will talk about the dereference trait, or just by specifying A, which is the box itself, and that's because box is implementing a display trait. And then obviously Rust is destructing the things on the stack. So it injects the code that is gonna be calling special thing, and that's not the trait, drop trait that we're gonna be talking about, because this is the box, which is magic, and it will basically destroy the variable A that points to the box with the array. That means it first removes the stuff on the heap, then the box itself, then it returns deletes the p box, returning the heap contents and the box itself. And if you think about it, so box is kind of similar to the unique pointer in C++. Obviously, if you have mutable or non-mutable box, then that would be a unique pointer to the const point. If it's a mutable box, then that would be corresponding to the unique pointer of the point itself. The differences obviously are that if you dereference box or move out of the box, then Rust will stop you from, the borrow checker will stop you during the compilation from trying to use that particular box variable, whereas in C++, maybe static analyzer will help you. Outside of that, you would be still able to try to access the unique pointer and then potentially crash or undefined behavior. So just talking about the box, what we would be able to use it, right? So why not keeping everything on the stack? And like one of the advantages of using box is that you can basically move a large amount of data without copying it over. And then the other thing is to break cyclic dependencies. So basically, if you want to create something and you don't know the size of the types, you can have a way of indirection to that particular type with the box. And also, you would use box if you want to own particular values, but you don't want to really know the specifics of the value. You just wonder about implementing a trait. And that's dynamic dispatch. That's dynamic dispatch that we will be talking about in chapter 17. So we're not going to cover it today. And just thinking about it. So in the book, they say that basically box doesn't bring any penalties. And it is almost true, I guess. So on the stack, you get extra size, obviously, that corresponds to the box, but it is kind of small. Then you have extra indirection, for which you pay non-locality of the data, because first of all, you would be accessing stuff on the stack, and the stack access is always in a cache. But then the things that is in the heap, not necessarily is going to be on the inside the cache, and then anyway you have to dereference. Yeah, and so if we're talking about the first issue that box is trying to help us with, so moving around large data. So the example is here, where we basically create an array of big array 10K, whatever, maybe it's not that big, try to print its data, and then we say, oh, we want to start a new thread. We haven't talked about threads, but this is like the minimal example, really. I can prove that moving around with the large data. So you would try to do some work on the different thread with that data. And like you would just say, hey, move it to the thread, do the work on the thread. And that work on the thread, for instance, is checking the pointer. and then you would be joining the thread. And if you print those two things, you would see that the data address that the array refers to is different. And that basically means when we move the data from this, from the scope of this function to the thread, it did the copy of the array. And, you know, like it's not necessarily problematic with the 10K that we just did here, but it might be, problematic if you, for instance, have much bigger data. If that data is already somehow computed and maybe filled in, that wouldn't make sense. But if you had to do something to basically create the resource, and that was the compute of that was taking long, right? So basically, those are the different addresses, and such a situation is causing the copy. And then, if you were to use the box, that situation is not going to happen. So you would create a box, you would print the address. You can see that we're dereferencing and then taking the address of that. Then printing the address of the box inside the thread, and the output is that it is the same box. So basically, if you want to pass on the data between the threads, pass on the data between the functions, then the box is really good about that. Then the other example that the book is giving us is basically enabling recursive types. And the example that they gave is about the cons list. That really is a data structure coming from functional languages, where it's a container that is built up from the value and the reference to another pair of value and the pair. And you can change them to those pairs basically to get the container. And yeah, so the cons value is basically looks like this, or cons list looks like this. You have value, then you refer another pair, and then eventually you would be terminating that with some marker, which they call nil. And the advantage potentially is that you can reuse parts of those lists to create another list. So you would end up with a list of X of values 2, 1, and then list of Y of values 3, 2, and 1, right? And that looks kind of trivial, but if you think and try to write the most simple Rust code for it, so basically you would try to encapsulate that in the enum, where you would say, either I have a cons element that points to integer value, we're not doing generics, and a tail of the list, or nil element. So you would try to construct it like this. Then what would happen is the compiler is going to scream at you. And the reason it's going to scream at you, it's obviously explaining that. And it's saying that if you're specifying enum like this, there is a recursive without indirection. It's suggesting you what to do, but it's basically saying there is a cycle detected and the type would end up as the infinite size. And if you think of it, why it would be why such a situation is not possible, then basically, if you look at the enum, what the enum is that it's a size that is going to contain maximum of the things, the variants that you would have in it. So it would be something like a size of integer plus the size of the same list, or the size of nil, plus probably the thing that is going to be a discriminant, what type of variant you have in the current instance of the enum element. And if you think of it, so your list should be able to accumulate all of that. And probably like in this scenario, the size of nil doesn't matter. So you would think that the size of list must be larger because it's a container, must be larger than size of int plus size of list plus size of discriminant, which would basically suggest that any size of which is not 0 for an int and discriminant is not going to satisfy that situation. What they say in the book is that you would end up with like that cyclic thing that you would want to enlarge and enlarge and enlarge the cons element, and that would never satisfy. So what are the alternative options? Like in the case of the simple code we have written in the main function above, you would come with a solution with generic data types, using generic data types. We haven't really talked about them, I think, in the book. So I have an example, we can share that, but I'm not gonna talk about that either. But basically, like in C++, you would be doing something like tuple, implementation of standard library tuple implements. So you would, every time you would have a bigger and a bigger list that would end up as a different type given by the automatically generated by the compiler. And that is good if you really specify constants in your code. It's not good if you're gonna be taking those constants dynamically from somewhere. And then the other solution for such a scenario is if you replace the variant that is giving us a problem with a variant that has a known size. And they did, so the compiler did suggest us what we should do. And basically it says that we should embrace list inside the box, because the box has constant size always. And then it's pointing to the list element that does that then, as specified like this, will have a constant size as well. So in this situation, when we use the box, what we basically end up with is a list of the tail being a nil, like this, with the discriminant pointing that this enum instance is a nil. Then that is gonna be wrapped with element 1 pointing to that nil, and then that's gonna be again wrapped with element 2 pointing to that nil. In this scenario, which is probably good maybe to think about, we would end up with the list itself, so the head being on the stack, and then everything else being on the heap. All right, so that is box. And then in the book, they said, oh, but you know what, let's make a diversion, because we need to talk about what makes smart pointers smart. So what enables in the language smart pointers being smart. And basically, there are two traits that most of the smart pointers implement. Those are deref and the drop. So first, we'll talk about the deref trait. And that trait allows treating types like references, which is very useful because then it's making your code using smart pointers easier to use and easier to access the data behind those smart pointers. It will give you uniformity in writing the code, as the uniformity of writing the code as if you wrote that code for references. And obviously, because of that, it makes your code easier to generify. And then what we will talk in a second, because of the coercion, it helps you write less boilerplate in your code in particular context. And box is one of the types that implements deref. So if you have a look at the example of using the references themselves, where you just have x pointing to integer, then you take reference y to that 5, and how you would be using it with assertions, for instance, to equalize. Then even though you use the box, the usage is the same. And the reason for that is box is implementing deref trait, right? And in fact, if we're talking about the deref trait, what happens if you're trying to use the so deref really, or when they refer to deref trait, they are going to be talking about two traits, which is deref and mute deref, deref mute. And basically, what they're saying is that when you are trying to use your smart pointers that implement the deref trait, with the dereference operator, then what it really gets to is the compiler unwinds it to such a call. So calling a deref from the, which is a method on the deref trait, and that returns a reference to the associated type of the trait, and then it would so the compiler would also deref it to get the part to get the value. And this is, so in the book they also say this is needed, that we would be returning a reference because of the borrow checker. If we didn't return a reference but wanted to return a value so that the compiler doesn't have to add that asterisk there, obviously we would be potentially moving out the value that is stored by the box, outside of a box, and that's not what we want. And in the mutable context, then we would be trying to use a RefMut trait that requires deref for that particular type to exist already. And then the compiler usages to the smart pointers that are trying to mutate the value inside the smart pointer. Then the usage like that would be basically by the compiler seen or rewritten to something like this. On the value, there is a smart pointer called RefMut, and then dereference it to modify the contents of the trait. So, like, because that's C++ Rust, right? So it kind of seems similar that if you're thinking about the deref traits, it's basically this similar as if in C++ you would be overriding operator, dereference operator and arrow operator for a class in C++, whereas for these constant operators, right? Whereas for RefMut, it's as if in C++ you would be overriding the non-cons versions of the dereference operator and arrow operator. So just kind of similarity that I think might be useful for some people to think about. All right, and then in the book they also mentioned that, by the way, if you implement, so if you have a smart pointer and you implement a deref trait, there is something kind of cool that we're giving you for free, and that's implicit coercion. And obviously that only works if you're implementing deref and RefMut on the type. This should be only implemented for smart pointers. And unlike in Rust, that coercion is going to happen implicitly. And the reason, so Rust is trying to be explicit so that it doesn't, or it makes you as a developer aware of what is being done. But in case of a deref, most of the time, what the deref implicit coercion is doing is what you would expect, but it helps you in reduce the boilerplate of your code. And that coercion will happen in context of methods, functions, and variables associations to with explicit types. And what we mean is that, for example, string is implementing a deref trait for associated type string, which basically means if you have a string, you would be able to call functions and assign it to to variables that are expecting reference to a string, and that would be done just with the take reference operator. So you can write a short code like hello, hey string, get me the address, right? And what the compiler would translate it to during the compile time, so you're not hitting runtime penalty, is that it will try to call a deref operation on the string to get the reference to a string. And obviously, that also holds for association with variables that have explicit type. So if there is a variable with the explicit type, that can be dereferenced from the string, then the compiler will have no problem in doing so. And what is also nice about that implicit coercion is that so it works during the compile time, but it also may happen multiple times. So it's not that it will only compiler will try doing it once, but for instance, if you so box is implementing deref and string is implementing deref trait as well. And in the example, if you, for instance, wrap string inside the box, you still can call that function that is expecting string reference just by calling hello reference s. And the reason for that is that Rust compiler will try dereferencing the box once, then it will see, okay, that type that it got resulted in that deref is not convertible to, or is not compatible with string reference, but the string reference that I got from the first deref, it implements a deref again. So I will try that, and it will try and try and try until it finishes all the derefs, or it matches expected input from the function. And again, that works for function calls, and that works for association assignment to explicitly stated variables with explicitly stated types. Yeah, worked for methods, but deref might have a problem, and from what I read, it might be abused by some people to simulate object-oriented programming inheritance. And because of also of that, sometimes you could consider, instead of calling the method, so let me go back. So if we go back again to that boxed string, when you're calling a method that is implemented on both, for instance, or multiple of the things that you can deref to, you not necessarily are sure what method you're calling. That's why they're suggesting to call it explicitly. So saying, hey, I'm not gonna be really calling some unknown len. I want to call len that belongs to string, or len that belongs to str, which obviously in this case is gonna be the same, but well, that's not necessarily the case with the clone, right? And from what I read, people are sometimes using deref even though their type is not a smart pointer, and they're doing that so that they can be calling particular methods just to mimic the object-oriented inheritance compile time. In case of deref, there are three interaction cases for that, for the mutability context. And basically, if you have a type T that implements the deref with the associated target type U, both of them not being mutable, then that's gonna work for you. If you have a type T, mutable type T, that implements a deref mute for a target U, then you would be able to convert it to, or to deref it to the mutable U. But in case you have it mixed, so for instance, you start with the type T mutable that implements deref with the target U, then you can convert it to deref U, to reference of U, sorry, but you wouldn't be able to do it the other way around. And that's, again, because borrow checking rules. And just a simple, quick example of what you should do if you want to implement a deref trait on your custom type. That's taken from the book, obviously. So in their case, they just define a smart pointer called myBox, which is not fully functional as the box itself. And that basically is a tuple with a new constructor function. And then they basically say, we're going to be generically implementing a deref type for myBox_t with the associated type of whatever is held inside that box. And because it's a tuple, I'm going to be returning a reference to the first element of the tuple. And if you want to implement a RefMut for the same box, that already requires you to have deref implemented, and then you implement the function RefMut that returns a mutable reference to the inner type. The other trait that they talk in the book is the drop trait. And that trait basically, when implemented, allows for customization of what happens when the value implementing that trait of the type, value from the of type implementing that trait goes out of scope. And it's basically almost always being used with smart pointers. And as you probably all are aware, it's a kind of equivalent of C++ destructor, right? So in case, and they again give an example of a structure with a string inside of it, structure being smart pointer, they implement a drop trait for a smart pointer. And then when they create the first smart pointer and then the second smart pointer, so that's the example, right? They create one and the other one. And then without any extra logic, on the console output, when you run this code, you will be able to see that those smart pointers are being dropped or distracted with the drop being called in the reverse order as they were created. And this is exactly the same behavior as you would have for a C++, right? But in case of C++, obviously that would, the structure type would have to implement the structure itself. So what is kind of different for drop trait of Rust with respect to the C++ destructors is that you can call early drop, and the early drop comes from, I didn't fully scope it here, but it's like from sys or sysmem drop, I think, or opsmem drop. And basically what it does is that it makes your code or the runtime not waiting for the variable to go out of scope to call a drop on it, and but it will destroy your variable or call the drop function for your variable in the place where it was called. And in fact, this drop is no magic. It's just an empty function taking a value of the variable being passed into. So the value is being moved into the drop function. It's not nothing is being done with it. So then it's just gonna be destroyed as the drop goes out of scope. And yeah, so we can see in this particular scenario, the drop is gonna be called before that print statement. And in the C++ kind of counterpart of it would be, for instance, with the unique pointers. So instead of having that smart pointer, in this case, that guy would be on a stack, right? In case of the unique pointer, that guy would be on a heap. But then with the unique pointer, you can move out your data from the unique pointer and just destroy it. Yeah, it's kind of the different behavior or different implementation stuff would be held in different parts of the memory. But if you really, really wanted to have similar behavior, then the closest you can get is unique pointer or some kind of pointer around your structure that you want to drop early. Again, the difference is that borrow checker will not allow you to use that C anymore after that call, whereas with C++, you can use moved out value however you want, maybe with some warnings from the compiler or static analyzer. All right, and then the book is moving to reference counting. And reference counting is, again, smart pointer that keeps reference count resource on the heap. It's used when you want multiple readers. So for instance, multiple owners of that resource being hidden by reference count. So RC holds immutable data that cannot be changed. And if you think about that, then RC kind of reminds of shared pointer to the const type in C++. So if we are reconsidering this the scenario about the const list that we were talking just earlier. So now in the book, they expanded usability of the const list implemented. So now they say, hey, we really want to do what we want, what the const list is about. So we want to be able to join them together, creating new lists. And if you were to use the same implementation that we just had before with the box and try to do that, then basically you would be trying to create a box that points to that data, but we said that box is not able to share the data, and then the compiler is gonna scream at you, right? So the compiler is gonna say that now you moved out your one const list head to a box, but you're trying to reference it somewhere else in the code later on. So we would have to do something about it. And this is where RC comes into play. So we would basically replace box with RC, and almost the same implementation as previously would be able to satisfy your needs. It's just right now, obviously, instead of a box new, you would have to get every enum instance into RC new. And then when you want to share RC pointers, then you need to call RC clone function. And the suggestion is, the good practice is that you're not calling a.clone, but you're calling rc.clone. And the reasoning for that is calling that makes no suspicion to the reader of your code. Whereas if you're calling .clone, then you're not necessarily sure which clone function you're calling, and that can raise suspicions that potentially that operation is expensive. RC clone is not expensive, right? Yeah. So in this example, when we are on the first line, we are creating RC to a new list. Then we're creating RC to the list holding element 1 with the reference count pointer to that nil element. Then that's also creating const element with value 2, with the RC pointing to the first or to the element holding 1, which holds element to nil. And our A is RC to that particular header, to that particular head. RCs are reference counted. That's why in this particular graph, I'm holding here information about shared count. And then if you would go to the second part of the code where you're trying to join those const lists together to create a new list, then basically what would happen is that element with the value 3 would have a shared, or would point to the shared count, to the RC element of the list with the element 2, and the reference count on that one will raise to the value of 2, right? Then you normally can use them, and when going out of scope, again, element B, list B would be distracted. So the reference count on value A would be dropped to 1. And then as A is being destroyed, reference count on RC drops to 0. it destroys that list. And because it just destroys that list element, this value is being dropped to 0, it destroys that. This value is dropped to 0, it destroys that as well. So everything is cleaned up as it should be. So that was const list containers. And we go to the last smart pointer type, which is RefCell of T. And RefCell is kind of special because it allows for a pattern in Rust called internal mutability, where you can mutate data even though the reference is not mutable. And that kind of should raise an alert in everyone who's learning Rust. But it's not that bad because the RefCell is the single owner of its data. And basically what it does is just works around the compile time borrow check invalidation, and it does the same borrow check invalidation, but inside or during the runtime. So RefCell is said to be holding immutable data, but then it can act on it in a mutable manner, right? And basically, it's useful when you're trying to write a code that you're pretty sure that it doesn't violate the borrowing rules, but you cannot really tell it to the compiler because compiler is trying to be really on the safe side, right? And when we're talking about the RefCell, then most of the time we're talking about using its borrow function method and the borrow mutably method, one of them written in the reference or ref element, and the other one written in the ref mutable element. And basically, that is a smart pointer around the T element that you would be able to refer to the data in non-mutable way that is held in the RefCell. If you're using RefMut, then you would be able to mutate the data that is held in the RefCell. And yeah, the way how you would be using the RefCell is that you basically create a RefCell around some resource, then you can borrow it in a mutable way. And if that mutable reference goes out of scope and is being deleted, then you can borrow it again in potentially non-mutable way. In case if you were to do it differently, so you create your resource in the RefCell, you borrow it, you keep the borrowed element reference, and then you try to borrow it mutably. So like the compiler in normal references case, it would raise you compilation error. And in this case, the runtime would raise you a panic, right? And similarly, so the same scenario basically, if you hold the if you hold the mutable reference to the thing held within the RefCell, and then you try to get another reference to it, but in a non-mutable manner, same as the borrow checker during the compilation time, the RefCell would raise a panic. And they're giving a nice example, I guess, for the RefCell when you would be willing to use it. So they give the example of production code where they have a messenger trait that is being used by the production code in the limit tracker, and they want to basically they pass to the limit tracker that something implementing the messenger with some configuration values, and then the limit tracker has a particular logic that when you call on the limit tracker set value things, set value, depending on the configuration that has been passed in the constructor of the limit tracker, it will send different messages to the messenger itself, right? So their explanation is we want to test the limit tracker. And the idea how they would want to test it is basically they want to test the collaboration with the messenger. So they want to introduce the fake double. They call it mock messenger, but I think it would be called normally like a fake double. Anyway. And basically that mock messenger, when it implements the messenger trait, it implements the method. And what they want to do is that when the limit trackers calls send on the mock messenger, then they just basically want to keep a list or keep a vector of the messages being sent, and then they want to validate. After running the test, they want to validate if those messages kept in the mock messenger they have appropriate size as they would be expecting it. And it all looks fine until you get the compilation error, which basically says, hey, the trait on the or the messenger trait implements a method taking a non-mutable reference to self. So you cannot be modifying things inside the self itself, right? And if we're having a vector, then we're really modifying the self. So then they basically say, this is the use case for internal mutability. And the way how you would be doing it is that whenever you have this thing that you want to modify, in this case, it's the vector of the sent messages on the mock messenger, then you would wrap it up in the RefCell. And then obviously adjust the code where you set sent messages. Then you need to create not the vector, but the new RefCell to the vector. And when you're really trying to modify internally a non-modifiable, non-mutable object, then you need to call borrow mutably to get a reference to the mutable vector held in it. And you would be able to do it without violating compiler borrow checker rules. And when you want to check the content of the messages, so you're sure that you're not going to be modifying the vector, then you can just call borrow to get a non-mutable reference to the vector and do validation on it. Just do the read on it. And this, again, in comparison to the C++, if you had a const structure class and you would have a member variable in it, which is like a stud vector, you would want to modify it, then either you would have to mark it as mutable member, or you would have to introduce some kind of reference, so extra indirection via the pointer or the reference to be able to change it and not violate the const correctness. And the RefCell is also being able to, in conjunction with the RC, to not only allow the multiple owners, what RC is giving you, but it is able also to give you an option to RC to hold the mutable data, even though RC is thinking that it's not a mutable data. And the way how they giving an example of it is that, again, we're going back to the const list, where you're basically saying, by the way, the value I'm holding in the const list, I want to be able to modify it. So instead of just I32, they're wrapping it up into the RefCell and into RC, into the RefCell because they want to modify it within the RC that wants to have multiple owners. If we want to have multiple owners, that value held in it, right? With the example that basically we are creating a value held in us in the cons that is going to be stored in one of the tuples of the cons list. Then we would be creating the cons list, another cons list that also references to the original const list. And then if we modify the value in the mutable way, then when we are printing it, we are still modifying the two values in the both const lists that where we holding that value. And yeah, that would be everything about the RefCell, everything. And then the book is moving on to an issue that you can get with the reference counted resources, which is namely memory leaks. And again, they're going back to the everlasting const list example, but this time they're going back to the version where we didn't modify the values, but we stored the mutable or multiple owners mutable data. They introduce also the tail method on the list so that they can get some element from the const list. And then they give us example where basically they create one const list containing of null and 5, and then the other const list. So one const list contain of null and 5, and then the other const list, which is referencing the first const list with the value of 10. So this is an error, that should be 10. And then when we are referencing with that B const list, when we are referencing const list A, then obviously the reference count on the element held by A is popped up to 2 from 1. And inside the example code that they're given is, and that's why they have introduced the RefCell, they say basically, hey, we want to get a tail, and inside the top element of the tail, we want to modify it mutably. So this is gonna be the first element of the tail. So we're gonna be modifying it mutably, and basically, instead of pointing to the nil, we want to repoint it to the B element, right? So obviously that drops the reference to the nil element. That element would drop to 0. It would be destroyed, and then it would point back to the B element, which would pop up the value to of the reference count to 2. Then we would be going out of the scope of the function. In this case, it's main, but that could be any function really. So it would destroy the B and A references, getting the reference count to 1. But still, you can see that we would end up with the infinite, or with the loop, where each of those reference counted resources still have the strong count set to 1. So they would not delete the resource. And we would basically end up with the memory leak. In this case, because it's the main, then the operating system would clear up those resources in case of at least the integer values held in those resources, right? So it would clean up it, and that wouldn't be a problem. But you can also imagine that this main function is any kind of function inside the business logic of the application where we would leak. So if they also are suggesting that in that example, you can uncomment the code, and because our const list is implementing the debug trait, we would be able to print it. And normally when you were printing it, that would be all fine. But basically we're running out of stack. So we're doing the Stack Overflow with such a print because the runtime is trying to print one and the other and then back one and so on. Yeah, and obviously this is a problem, right? And one of the ways, or Rust is basically saying memory leaks because of such an example that we've seen with the RC is not detected by Rust, and it's not intended to be detected by Rust. And those are considered to be logical errors. which you should really detect with tests or during the code reviews. And you can also do some extra stuff if you wanted to prevent them, because there are situations where you kind of need to have those cycles. And in such a case, you can use, again, reference count, but using special values of the reference or special types associated with the reference count, which express ownership in terms of we have referenced something which is owning reference or not owning reference. Unfortunately, they also mentioned that it wouldn't solve the issue with the cons list, because one list that points to another list wants to own that list as well. But there are situations where you can use those particular types. And we'll go through such a case.
Just before you do that, Krzysztof, sorry, we have a question in the chat from David asking if these memory leaks are detectable by as-an.
Address sanitizer, you mean?
Yes.
I would expect them to be detected by address sanitizer, right? Because eventually, even if you're using the they are allocating stuff or memory on the heap, right? And as your application is exiting, an address sanitizer would have information they haven't been freed, right? So I would think so, but I haven't checked it, right? Yeah, so that's the only really answer I can give. Anyone else maybe has the answer to that?
Good question, David.
I mean, like Valgrind would be able to tell so, right? To say so. So yeah, I guess it is possible, right? The problem with this scenario, like always, is that as your application logic is getting more difficult, right? More complicated, you not always are hitting the case where you would be experiencing the cycle, right? So obviously running the address sanitizer with during your tests or at some stage of your tests, and if your tests have pretty good code coverage, but then the branching coverage as well, right? Then you should be able to detect it. That's my guess. All right. Yeah, so again, to fight with the memory leaks, we would be using a reference count, RC, but then RC has special methods when you can call on an RC a downgrade, whereas you would get a weak reference pointer to your resource. And then if you want to use such a resource that is referenced with the weak pointer, then you would have to first call on the weak upgrade to get it to the option of the RC. And obviously, if the resource was already released, then the option would be none. Otherwise, it would be some of that RCT, and you would be able to use it. And again, if we're thinking in C++ way, it is kind of similar to what the shared pointer and the weak pointer is giving you. It's just, again, the weak pointer, when it is to be upgraded, it would give you a shared pointer, and the shared pointer could be null, right? If it's not pointing to the resource anymore. And so, as we said, it's not gonna help you with the cons list, but it is usable in some other aspects. And their example is basically a tree where you have a node of every tree holding a value, and then the reference to a list of nodes. So those would be RC, which means shared owners, vector of shared owners nodes, and then RefCell because you can modify the vector, right? With the with the RefCell. With the example, creating a node of the value 3, which is a leaf, that would be pointed by the leaf itself, and then creating a node that is a branch that is pointing to one of the children to the leaf, and that's why you would be getting on the leaf you would be getting a SC of 2. So this is not a cycle yet, but if you wanted to have a tree that is introducing in nodes a reference to the parent itself, then it's a situation that would be problematic potentially. It's a it's funny because there is a code that is hidden by the output of that code, but basically you wouldn't be obviously using RC to point to the parent, but you would be using a weak to point to the parent, and when you want to refer to the parent, you would be upgrading the pointer to the parent to be able to refer to it. And like the example given in the book is nice because like they're not really explicitly referring to a parent itself in the example, but they're trying to print the parent or print the leaf. And because the leaf is implementing the debug, it will print all those elements in the node itself. And you can see that it's not really printing weak references, but it's only printing the strong references to the elements. And again, this is good because it could potentially dereference something that doesn't exist anymore, for instance, or would again get into the cycle. Yeah, so just as a summary of what we just said, right? There are different simple shared pointers in Rust, and you would use them in different circumstances. And depending on your requirements, like if you want to have multiple or single owners, you would use RC if you want to have multiple owners. You would use box or the RefCells if you want to have single owners. But if you want the mutability, then you would use box, the immutable or mutable, but with a single owner, RC in the immutable context for multiple owners, and the RC when you want to check it at compile time. And then the RefCell, if you want immutable or mutable borrows, check in the runtime, right? And just a note again, there are lots of instances where you are kind of wrapping one RefCell, RC with the RefCell or the other way around to get the immutable shared references. And that would be it. And yeah, as Alex, I guess, said, this is kind of beefy, right? So I thought it's gonna be easier to present. Hopefully it wasn't that bad. But one of the things that I found really useful, apart from the book about the shared pointers, is just to go to YouTube channel, Crust of Rust, where Jon is trying to implement some of the smart pointers, and it's implementing also the interior, showing how interior mutability is working really. So that was kind of useful, at least for me to understand it. Hopefully that wasn't too bad.
Thank you very much, Krzysztof. That was a very hard topic to cover, and I think you did it brilliantly, especially under the initial difficult circumstances as well.
Yeah, it caught me off guard a bit. and it wasn't just that person, right? Also, my boy just came in banging at me. Oh boy.
Oh dear. Well, dealt with it excellently as always. Does anyone have any questions for Krzysztof while we're here?
Krzysztof, great talk. Thanks for working through all of that. There was a lot of it.
Yeah.
I've been wondering before on Rust, before we even got to this chapter, about how you would have a structure where you wanted to mostly to appear to be immutable, but internally it would maybe store something the first time it was requested. So you'd have like a just-in-time cache for an expensive calculation. So in C++, we'd use mutable on a member variable. So is the only way to do it in Rust to use a RefCell?
No,
Or
I think it's
something.
I think you can also use something like unsafe code, right? And then you would be. But no, I can't really tell you that, right? I'm not too specialized really in Rust to be able to say so. I mean, there are different shared pointers as well, right?
You couldn't, for instance, just use the mute keyword on one of your data elements inside the structure, which was my first thought. I think I tried it and it wasn't very happy about it.
No, so that is already caught by the borrow checker, right? Which is good. It's during the compile time quick feedback, but not that. I think it's only via that. Mutability thing, which I forgot name of.
RefCell, the internal mutability.
Yeah, but potentially, I mean, if so I'm not sure if there are like different shared pointers in the standard library that can enable you that, right? There are crates with the different cells that can also enable that, and then they have different features. But yeah, I haven't really worked with that, right? So I cannot give you an exact answer what you should use.
Yeah, no worries. Thanks.
There's a type called a once cell as well, so which is like a RefCell a little bit, but it only gets initialized once.
Ooh, I like the sound of that.
But I don't know if you can include it in a structure.
Right. And I guess that would be a runtime check that it does to make sure it's not trying to be reused. Yeah, worth checking.
If there's no more questions, there's a small bit of housekeeping to take care of. Can everyone see my screen okay?
Yeah.
Excellent. Yeah, so the end is in sight. We've got just 5 chapters left. So next time we'll be tackling fearless concurrency, which I believe Kira's scheduled to do that one, but I will double check with her. And if anyone else would like to have a go at following Krzysztof's lead and taking us through a chapter, I've put all the details in the chat for getting in touch with us. Feel free to just shout out. And some other dates coming up. So fearless concurrency with Kira on the 17th of February. On the 23rd, we'll be going back to having our more free-form meetups where we've got a talk arranged. Richard is going to take us through a C++ related talk, implementing an enigma, which is delightfully mysterious. And then a short time after, we'll be tackling pattern matching and advanced features in Rust for another Rust book club on the 3rd of March. So exciting times ahead.
One day we might be able to meet up in real life.
Yeah.
Yes, maybe.
I got my booster on Tuesday and I didn't feel great. I was a bit worried that it could jeopardize the presentation, but it was, yeah, today is good.
It was everything else that jeopardized it this time.
Yeah, but so I went to, or I did work remotely yesterday, but at the middle of the day, I just said I couldn't. Needed to go to sleep and just. Yeah.
It's important to rest up when you feel like that. Right, well, I'll ask one last time if anyone has any questions for Krzysztof, but if not, see you next time on the 17th.
And again, I'm not an expert, right? So if maybe there is someone who can say I like lied, right? Or I didn't say something well, I'm very happy to be corrected, right? Because that's also the knowledge I will have for the future.
Yeah, that's exactly why we're all here.
Yeah, I'm not an expert on Rust, so
Yeah, that's worth stressing.
Presentation should be taken much less than it did, like always.
You have touched an important point there, Krzysztof. When we ask people to lead the chapter, they don't necessarily have to be experts. All they have to have done is read the book and worked through the chapter in question, and they can come with their own questions. You don't have to be an expert to lead the club.
You always start from somewhere, right?
Exactly.
But yeah, the presentation, getting to the presentation is much better than just reading a book in terms of trying to understand it, right? So it is useful.
Definitely. I think both forcing yourself to read it so that you can present it and watching someone else explain it makes it a much more active process than just quietly reading it yourself.
Even if you read it and watch it, right? You already gone through the material twice, which is how people are learning anyway. Like that's what we would do for the exams, right?
Yeah.
All right then.
Gotta go, chaps.
Yeah. If there's nothing else, I'll call this an end.
Thanks again, guys. See you again soon.
Thank you, guys.
See you next
Bye.
time, everyone. Bye-bye.
Have a good
Thank
evening.
you. Cheers. Bye.
Cheers, bye.